What if every atom in your body, every star in the sky, every galaxy that exists are not actually made of matter at all? What if matter itself is just an illusion, an appearance created by something far more fundamental, hiding beneath reality? What if everything you see, everything you touch, everything you are, is built from something invisible and abstract? What if, at the deepest level, reality is made of information? We've been exploring the deepest mysteries of quantum mechanics for 4 episodes now. We've watched the future change the past. We've discovered that particles can be entangled across impossible distances. We've learned that measurement doesn't reveal reality, it creates it. And we've discovered that at the moment of measurement, the wave function collapses. Possibilities become certainty, but we still don't know what's actually collapsing. A physicist once asked the most obvious question: when a wave function collapses, what exactly is changing it? Is it matter? No. Particles don't have definite properties until after measurement. Is it energy? No. Energy isn't created or destroyed during collapse. The math shows this clearly. Then what? But here's where it gets interesting. When physicists examined what actually transforms during that collapse, one possibility emerged that was almost too simple to take seriously: information. Some physicists began to propose that when the wave function collapses, information is what fundamentally changes. Possibilities transform into facts. Uncertainty transforms into knowledge. But before we go further, we have to clarify what physicists actually mean by information, because it's probably not what you think. When most people hear the word information, they think of data, email, internet, a message on your phone, numbers stored on a hard drive. That's information in the everyday sense. That's not what physicists mean when they talk about information as fundamental. In physics, information means something more essential. It means difference. It's distinguishability, the ability to tell one thing apart from another. And think about a coin. Before you flip it, it's either heads or tails. You don't know which. That's uncertainty. When you flip it and look, you discover the answer. Heads or tails, that outcome is information. That one bit of difference between two possibilities. Think about a deck of cards. There are 52 cards. Each card is different. The existence of those differences is information. The Queen of Hearts is distinct from the Ace of Spades. That distinction is information itself. Think about a book. Every letter on every page is information. Each letter is different from blank space. Each word is different from random characters. The information is what creates meaning from chaos. Now think about DNA. Every living thing on Earth is built from DNA. And DNA is fundamentally a code, instructions written in molecules. 4 chemical letters arranged in a particular sequence. That sequence contains all the information needed to build a human body. A lion, a tree, a bacterium, different sequences, different information, different life. Everything in nature seems to be built from distinctions, from differences, from information. And here's what became fascinating to physicists. Information has properties that are fundamentally different from matter and energy. According to classical thermodynamics, information cannot be destroyed. You can burn a book and destroy its physical form, but the information isn't gone. It's encoded somewhere in the universe, in the ashes, in the smoke, in the radiation released. In principle, if you had perfect knowledge of every particle in that fire, you could reconstruct every word. The information persists. This observation led one of the greatest physicists of the 20th century to ask something genuinely radical. John Wheeler spent his entire life studying physics. He worked with Einstein. He mentored Richard Feynman. He was brilliant. And in the 1980s and 1990s, near the end of his life, Wheeler proposed an extraordinary interpretation. He suggested that information might not be merely a property of the universe, but what if information were actually the foundation? What if it were more fundamental than matter or energy? He called it from bit. The phrase came from a simple observation. Every physical thing in the universe might ultimately come from bits, from binary information, from yes or no, from 0 or 1, from distinctions themselves. What led Wheeler to this idea? He noticed something crucial in quantum mechanics. Before measurement, nothing is real in a classical sense. There's no definite position, no definite momentum, no definite property. The only thing that exists is information. The information encoded in the wave function describing all possible outcomes. When measurement happens, that information transforms into a definite fact, but the mechanism creating that fact is still information. Wheeler wasn't claiming he had proven this. He was proposing an interpretation that made philosophical sense of what the math was describing. He believed, or at least seriously entertained, the possibility that reality could be built bottom up from information, that information creates the appearance of matter and energy, that at its deepest level, The universe is not made of things, but information about things. It sounds like philosophy. It sounds abstract. And that's because it is in many ways still at the boundary between physics and philosophy. But Wheeler grounded this idea in quantum mechanics itself, in the way the universe actually behaved. Here's his reasoning. In quantum mechanics, the only thing that's real before measurement is information. Possibilities exist as information. The wave function is information. When measurement collapses the wave function, information transforms into definite facts. But throughout the process, it's still information. So what if Wheeler was on to something fundamental? What if there is no deeper layer of matter beneath the information? What if information is genuinely the bottom layer? This would mean that reality is participatory in a deep sense. The universe would exist as possibilities, as information about possibilities until something interacts with it, until something asks a question. Then the universe responds with information, with an answer, with a definite fact. This interpretation created an intellectual framework, but then something happened that almost proved the whole thing impossible. In 1974, Stephen Hawking made a discovery that sent shock waves through theoretical physics. He calculated that black holes are not black, they emit radiation, Hawking radiation. And more unsettling than that, he showed that black holes eventually evaporate completely. They disappear. But this created a genuine crisis, a crisis we're still grappling with. If a black hole evaporates, it takes everything inside it with it. The information that fell into the black hole seemingly gets destroyed, gone forever, a loss to the universe. But here's the problem. Physics has a principle fundamental to thermodynamics. Information cannot be destroyed. The laws of thermodynamics depend on this. The universe's entropy, its disorder, can only increase or stay the same, never decrease. And that's only mathematically true if information is conserved. This became known as the black hole information paradox. And it's one of the most urgent unsolved problems in theoretical physics today. Why did this become such a big problem? Because if information can actually be destroyed in black holes, it means the very foundation of thermodynamics is wrong. It means entropy doesn't behave the way we thought. It means time might not flow in the direction we assumed. It means quantum mechanics and general relativity are fundamentally incompatible in ways we don't understand. In other words, if information isn't conserved, physics would need to be rebuilt from the ground up. For decades, physicists argued intensely about this. Some thought information really was destroyed, which would require revolutionary new physics. Others insisted it must escape somehow. Some thought the solution might require completely rethinking what space-time actually is. But here's what the ongoing debate revealed. Most physicists now lean toward believing that information is conserved, that it must escape black holes somehow, perhaps encoded in subtle correlations in the radiation, but the mechanism remains unknown, and this creates an even deeper mystery. If information truly cannot be destroyed, if every interaction leaves an indelible mark, then reality behaves very differently than everyday experience suggests. It means that every interaction you have with the universe leaves a trace, an imprint. Information about you becomes encoded in the fabric of space-time itself. Think about that. Right now, your existence is creating information, ripples throughout reality. Everything you've ever done would be preserved, in principle, forever. If you had perfect knowledge of every particle in the universe, at this moment, you could theoretically reconstruct your past. Every moment, every thought, every choice. In some sense, the universe is recording everything. Whether that information is ever recovered or remains forever inaccessible is still an open question physicists debate, but this observation led somewhere unexpected. Because if information theory contains any truth, if information really does underlie how the universe works, then information can be processed, manipulated, transformed, and that's exactly what quantum computers do. A normal computer uses bits, 0 or 1, off or on. Every calculation requires many bits to complete. The more complex the problem, the more bits you need, exponentially more. If you tried to simulate a quantum system with a classical computer, you'd need an impossibly large number of bits, but a quantum computer uses qubits, quantum bits. And this is where superposition becomes powerful. A qubit can exist in a superposition of 0 and 1 simultaneously. The power of quantum computers comes from this property. A quantum computer with just 300 qubits could theoretically explore more possibilities in superposition than there are atoms in the observable universe. Why? Well, one interpretation suggests that if reality is fundamentally built on information processing, then the universe itself explores possibilities in superposition. A quantum computer, under this interpretation, would be leveraging the same principle. It's letting possibilities exist in superposition while the calculation happens, then collapsing into the answer. Whether this means quantum computers prove information is fundamental remains something physicists discuss, but it's suggestive. And then we encounter an idea that takes this concept even further, an idea that seemed almost impossible when it was first proposed. There's a concept that emerged from studying black holes and string theory called the holographic principle, and it proposes something that seems to contradict everything we experience. Everything you see in 3 dimensions might actually be encoded in just 2 dimensions. Here's the analogy. Imagine looking at a photograph. A photograph is 2-dimensional, but a skilled photographer can create the compelling illusion of 3-dimensional depth, shadows, perspective, and focus. They all work together to create the perception of a 3-dimensional space on a flat surface. Now imagine that works perfectly. A projection so complete that there's no way to tell the image is 2-dimensional. That's closer to what the holographic principle suggests. Everything you see, all 3 dimensions, all the depth, all the space around you, might be a projection, a shadow, cast by information arranged on a 2-dimensional surface. Another way to think about it, imagine watching a movie. The movie is projected light, essentially 2-dimensional, but your brain creates the illusion of 3-dimensional space, and you believe in the characters. The story feels real, but it's all projected information on a screen. What if our universe works the same way? What if the 3-dimensional space you're living in is actually a projection? What if the information encoding all of reality is inscribed on a 2-dimensional boundary somewhere at the edge of the universe? This sounds like pure philosophy. It sounds absurd. But the holographic principle isn't speculative arm-waving. It emerged from rigorous mathematics. Juan Maldacena derived an equation showing that a 3-dimensional universe could be mathematically equivalent to a 2-dimensional universe with specific properties. It's one of the deepest equations in modern theoretical physics, and it doesn't prove we live in a hologram, but it demonstrates that dimensionality itself might be emergent, an appearance created by the underlying information. Now, let me be completely clear about what evidence actually supports these ideas, because this is where we must distinguish between physics and speculation. And here's what we know for certain. Black holes emit radiation, as Hawking predicted. That's been confirmed. The question of whether information truly escapes from black holes remains actively debated. Recent theoretical work suggests most physicists lean toward information being preserved somehow, but this remains unresolved. It's still an open question. The holographic principle has been tested indirectly through mathematical consistency with relativity and quantum mechanics. It's been found to be consistent in remarkable ways, but we haven't directly observed a 2-dimensional boundary encoding our 3-dimensional universe. We can't yet. Quantum computers are now real and they work. They demonstrate the power of superposition, but whether they prove information is fundamental is a different question. That they're consistent with information theory, but consistency isn't proof. So the information theory of reality remains what it is, a hypothesis, a bold interpretation supported by elegant mathematics and surprising internal consistency, but not yet definitively proven in an experimental sense. That's actually how science really works. We have ideas that explain surprising patterns. We test them in many ways. We see if they survive scrutiny. Information theory has survived scrutiny remarkably well, but honest scientists acknowledge what remains speculative. And yet, exploring where this idea leads takes us into genuinely profound territory. If information were truly more fundamental than matter, if it were the deepest layer of reality we can currently conceive, what would that mean for the most mysterious phenomenon we know? What would it mean for consciousness? Think about your memories. Your memories are information, patterns of connections between neurons. If the universe operates on information as its foundation, and you're made of information, then your memories are literally woven from the same substance as reality itself. Think about time. Time moves forward. Entropy increases. The future becomes the past. But what is time really? One interpretation suggests that time is the process of information being revealed. The future contains all possibilities, all information about what could happen. The present is when information transforms from possibilities into facts. The past is the accumulated information that can no longer change. But this is interpretation, not proven physics. Think about consciousness. Your awareness of the world is information being processed by your brain. Your sense of self is the integration of information. If reality is fundamentally built on information, and remember, that's still a hypothesis, then consciousness wouldn't be something alien to the universe. It would be part of how the universe processes itself. But whether consciousness is fundamental, emergent, or something else entirely remains genuinely open. Think about identity. You are not the same atoms you were 7 years ago. Every atom in your body is replaced over time. Yet you feel like the same person. Why? One possibility. You're not really a collection of atoms. You're a pattern, an arrangement, information. The specific sequence of information that makes you you would persist even when the atoms change. Think about what happens at death. This is the most unsettling question. If information cannot be destroyed, and remember, this is still debated, then the information that composes you, the patterns that make you conscious, would persist somewhere in the universe. Not in a supernatural way, not in an afterlife, but in the information itself, in the traces your existence leaves on reality. We don't know if that information is ever integrated into consciousness again. We don't know if there's any sense in which that persistence matters. But if information is truly conserved, information theoretically never truly disappears. These aren't idle speculation. These are logical consequences that follow from taking information theory seriously. They're strange, they're unsettling, they're beautiful, but they follow from the mathematics, even if the premise remains unproven. The universe is not made of isolated things. It's made of relationships, distinctions, connections, information, and perhaps, just perhaps, consciousness exists as the universe's way of knowing itself. Perhaps meaning emerges when information becomes aware of itself. We don't know if that's literally true, but we know it's a possibility profound enough to reshape how we understand existence itself. We don't know if the universe is made of information, but we're learning to ask better questions about what it could be. But here's what matters now. We've been assuming something fundamental about reality without questioning it. We've assumed that space is real and that it exists independently, that it's the stage on which information performs. That space is the container holding all existence. But what if that assumption is wrong? What if space is also made of information? What if the very fabric of space-time is emergent? What if it arises from something deeper? Here's where everything changes. What if space itself doesn't actually exist? Not in the way we think it does. Not as a container, not as a stage, but as an emergent property, an illusion, a shadow cast by something far more fundamental. What if space-time is an illusion? Not in the sense of not being real, but in the sense of not being fundamental. All around like a hologram is real, but is projected from something deeper. Some of the most brilliant physicists working today believe this might be true, and their reasoning is grounded in quantum mechanics, general relativity, and information theory combined. What if the smooth fabric of space-time we experience is actually woven from something else? What if distance itself is generated by quantum entanglement? What if space emerges from deeper quantum connection? What if the universe isn't a three-dimensional stage at all? What if that's just how our brains interpret something? Far stranger. Next time, we explore one of the most radical ideas in physics, an idea that suggests everything we know about the structure of reality might need to be fundamentally reimagined, but not because the old physics is wrong, but because we've been looking at the wrong layer of reality. What if space-time is not fundamental? What if it's emergent from something deeper? What if the smooth, continuous space we experience is actually made of discrete quantum information? What if everything we think we know about distance, time, and causality is just an appearance, a useful illusion? Join us next time as we ask the question that might reshape how we understand the universe itself. Is space-time an illusion? Metadata for you.